So folks, let's work through this problem right here. We're asked to evaluate a triple integral where this is our integrand, and we're told that the region E is the region beneath the cone and inside of the sphere. So let's go ahead and take a look at our region here. We've got this sphere of radius 6, and so I'll try to sketch that real briefly. Let's put the radius down here. So the radius is 6. And so our region has to be inside of this sphere, but it also has to be beneath this cone. So this cone looks like this. There's the cone. Z is equal to the square root of x squared plus y squared. Remember, because of that square root, and square roots can only output positive numbers, that this does not have the other part of the cone that goes down this way. And so if we were to look at this cone here, it continues on beyond the boundary of the sphere, but we only want this part of it. So we want to be below this cone and inside this sphere. So now that I've got sort of a general working knowledge of what this region looks like, let's try to sketch it a little bit more carefully. So I think that our region is going to look something like this. And I'd still like to make that just a little bigger. So one way to look at it, I think of it as a sphere with a hollowed out cone. If you'd like to see a picture of that, I'll put it up now. So while it's not essential to have a perfect 3D sketch of this, this is sort of like the region that we're looking at, where we've got, we're inside of this sphere, but we are below this cone. So it's like we've hollowed this out by the cone, and that's the origin sitting kind of right at the tip of that cone. So there's our region. So I think we're ready to start describing this region, E, in terms of rho, phi, and theta. So I think we should feel comfortable saying that our theta has to go between 0 and 2 pi. And I think we should feel okay saying the rho can go anywhere up to the boundary of the sphere. So our rho has to be between 0 and 6. That's the radius of this sphere here. Even after we've hollowed it out by this cone, you still can't have a rho value going beyond 6. Then the last thing is the value of phi. And phi is going to be bounded between two values here. So if we go ahead and put in our z-axis into this image, there's the z-axis. And remember that phi is a measurement of the angle off of that z-axis. So let's see here, I guess we'll do blue. So this phi doesn't begin until we get to here. This would be our minimum value for phi, because we don't want to include anything of where the cone originally was. And then our maximum value of phi is all the way down here to the value phi equals pi. Careful, folks, I for some reason have a really nasty habit of when I want my phi to be pi, for some reason I put pi over 2. That's the 180-degree span of phi there. So I think I feel comfortable saying that upper bound for phi is pi. But what is that minimum? There we're going to have to be a little more careful. If I were doing this question on an exam, I might jump straight to the answer. But here I'd like to be a little bit careful in deriving it just to make sure that we see why that's the case. So I'm going to restrict ourselves to the xz plane. In fact, let's maybe make that, so there's x and there's y. Let's go ahead and say to the yz plane here. So if I were to look at this curve, if I were to look at this in the trace in the yz plane, what I would have is, or even the projection, what I would have is something that looks like this. So that would be this piece right here as we project it down into the yz plane. And then we would have this our sphere running like that, and that's not the best picture, but we'll call that good enough. And then our hollowed out portion of the sphere would lie here, but what we're after this angle phi here. That's what we want to know. So notice that phi, the key here is to recognize that it's the that's going to go till it hits this bound here. That's the lower bound for phi. The upper bound is all the way to here. But we're trying to find this value of phi. So one way we could do that is to construct this triangle. So we're trying to construct that triangle right there to figure out what phi is. And the key insight is that that point right there for the triangle is going to give us the coordinates that we need to apply the arctangent to figure out what phi is. So we need to figure out those coordinates right there. But the key is that those coordinates are where the blue sphere, the hollowed out sphere, intersects with the green, the blue hollowed out cone intersects with the green sphere. So if we set the two, we look at the two, here's our green cone, x squared, or excuse me, our green sphere plus z squared equals 36. And here is our blue cone. And I want to solve that. I want to figure out what that, remember I'm in the, let's go ahead and put our axes back here. I'm in the YZ plane. So let's go ahead and try to first find the y coordinate. So if I were to take this equation and square both sides, I would get that z squared is equal to x squared plus y squared. And then let's plug that into that equation. So what we get is x squared plus y squared plus x squared plus y squared needs to equal 36. And so if we continue, we would have that 2x squared, in fact we could factor it, so say 2x squared plus y squared has to equal 36, or that x squared plus y squared has to equal 18. That tells us, if we plug in that fact into either of these two statements here, that tells us that z has to equal the square root of 18, or that z is equal to 3 square root of 2. So we now know that that coordinate there at that point of intersection, the z coordinate is 3 square root of 2. Then we just need to figure out what y is. Well, let's take, doesn't matter, let's take this cone here. If we are in the yz plane, then that is where x is 0, and we just said that y was 3 square root of 2, or excuse me, that we just said that z was 3 square root of 2, and so we can now solve for y squared. And if I do so, I get y squared is equal to, that comes out to be 18, so 18, so I get that y is also 3 square root of 2. If I were doing this on a test, I probably would have already recognized, folks, that this cone right here is the cone that has a 45-degree angle as it rises up, and so I would have already known what I'm about to say. But I just want to show you how you would do this in general, because that's not always going to be the case. So now we'll say that the tangent of phi is equal to the square root of 3 over 2 divided by the square root of 3 over 2, or that the tangent of phi is equal to 1. So phi is equal to the arctan of 1. So phi is a 45-degree angle, pi over 4 there. So all that work was done to find that lower limit of integration. So now that we've got that, I think we're ready to do our evaluation. So let me grab those two bits that are useful to us. Come on. So there's our image, and then here is our region. And let's erase that. So let's zoom in there. So now I think we're ready to go ahead and set up the integral. Oh, and as a reminder, the original integral was e is equal to, and then we had, I'll factor out the 5 over 776. And then we had x squared plus y squared plus z squared dv. So now we're converting this integral into a spherical integral. So this is going to be from theta equals 0 to theta equals 2 pi. it's usually most convenient to do phi next. So we'll do from phi equals pi over 4 to phi is equal to pi. And then our rho is going to go from 0 to 6. And then our integrand, the constant will remain the same, 5 over 7,776. Our integrand, this expression can be replaced with rho squared. And then we've got our volume component. And remember that for spherical coordinates, that's rho squared sine of phi d rho d phi d theta. So let's just clarify, folks. Here was our integrand. There it is in spherical coordinates. And here was our dv component. And there it is in spherical coordinates. Let me just make sure you were able to see all that. Yes, okay. So now I'm ready to go ahead and evaluate this. Let's take out the 5 over 7,776. And then we'll have the integral from 0 to 2 pi over 4 to pi 0 to 6 of rho to the 4th sine of phi d rho d phi d theta. One thing to point out, folks, is we've got this integral, this outer integral, which will be respect to theta. There's no way that a theta expression is going to show up in the first two iterations of integration. Because of that, we can say that all of this expression is just a constant as far as theta is concerned. And when you integrate a constant, you simply, over an interval, you simply get the length of the interval. So I can go ahead and pull out the length of that interval, which is 2 pi. So I'm going to say that this is going to be 2 pi times 5 over 7,776, then pi over 4 to pi 0 to 6, rho to the 4th sine of phi d rho d phi, having already taken care of that integration with respect to theta. Now if I integrate this with respect to rho, I end up with 2 pi times 5 over 7,776, integral from pi over 4 to pi. This is going to be 1/5 rho to the 5th, evaluated from rho equals 0 to rho equals 6, the sine of phi d phi. This is going to give me 1/5 rho to the, so 6 to the 5th minus 0 to the 5th, all times at 1/5. And so that just gives me 6 to the 5th over 5. 6 to the 5th is our 7,776. So that's really nice. What I'm saying here is that this will evaluate to be 2 pi times 5 over 7,776 times 7,776 over 5, where that was our 6 to the 5th power. So then we're just left with this, from pi over 4 to pi of the sine of phi d phi. Here, those two components are multiple reciprocals of each other. So we get 2 pi, integrating the sine of phi gives me minus the cosine of phi, and we're going to evaluate that from pi over 4 to pi. That comes out to be 2 pi times minus a minus 1 minus a minus square root of 2 over 2. There's sort of one more iteration of parentheses there. It doesn't really matter. And so then we're left with 2 pi times 1 plus the square root of 2 over 2. And I'll leave the pi outside, but I'll distribute the 2 through. And that's a nice way to mark the answer. Of course, this would have been fine, or any other version of the answer. Folks, I hope this was helpful. Let me know if you have any questions.